Hey class, problem 66 from chapter 11 is a pretty tricky one, and so quite a few people have been asking about it, so I thought I'd make a video. And I'm in front of a live recorded audience today, so if you hear any questions, hopefully they'll be helpful to you guys as well. Anyway, so we got this crazy situation where we got this block on a ramp starting from some height h, which is given to us, and it slides down until it collides with a rod, a vertical rod. Then it rotates up to some angle theta, which is shown to us in the picture here, and we're asked to determine what that angle theta is based strictly on really knowing the masses of our objects, the length of the rod, and the height that our object starts from. So what I really see in this case is there being a series of different situations or locations that we're going to look at. So we have kind of position 1 you can think of when the block starts up at the top of the ramp. You have position 2 here right before the two objects collide together. Then you could think of position 3 as being right after the two collide together and stick. I'm thinking of conservation of momentum because there's an inelastic collision where I know energy will be lost. And then there's situation 4 when our object has swung out to its full out position. So what I'm thinking, if I want to find what that angle is, I need to work backwards, and I see that I have an object swinging up from one position to another. It makes me think of conservation of energy potentially. Then I think of conservation of momentum with the collision, and working back, conservation of energy once again to figure out what momentum the block brings into the collision. Oh boy, that sounds crazy. So we got 1 to 2 energy, then we got 2 to 3 momentum, probably angular momentum, and then we got 3 to 4 energy once again. Oh, I forgot the 4. Oh, okay, sorry about that. Anyway, we'll just cross this out and write it over here. Okay, 3 to 4 gives us energy once again. But how are we going to use that to find the angle? I think a lot of people probably are confused about that. So I want to start there to make sure we understand what we're looking at here. So if we think, here's our rod when it's in the vertical position. It has a length L. Okay. Now when it swings out to an angle theta, we have the rod that still has a length L, and now we're at this angle theta, right? And so what you can see here is you can actually make a right triangle. Maybe I'll use orange here. I can make a right triangle here representing that angle theta in terms of L, the hypotenuse, and this new distance over here, which maybe we'll call the length of this side. Maybe I'll label it something like D. Okay, so that's the distance from the top to where the object, the block, which is down here, right, is when things stop. So the reason I want to use energy is because if you notice here, let me scroll down a little bit. If you notice here, our block has raised some distance above its original position. Maybe we'll call this H final or something like that. So it's raised some H final. Gravitational potential energy tells me that I should be able to find what this final height is that it's raised up, and you can see that that D value is going to be equal to L minus H final. So if we find the H final, we can find what our L value is, or excuse me, we know our L value, we can find what the D value is, and then if you look, we can see and observe quite simply that the cosine of our angle is going to be equal to D over L. So we can find our angle once we know D based on knowing L. And you can even make the substitution of plugging this in here if you'd like. You can say that the cosine of the angle that we're trying to find is equal to L minus this H final divided by L. Okay, sounds good. So all we need to do is find H final, and we have our L value. Piece of cake, right? Well, maybe not quite that simple. Let's take this one step at a time. So let's start by looking at our steps from 1 to 2. So at position 1, what type of energy do we have? Well, I see we have the small block, which is a lowercase m, times g, times this h initial that we're given, the height that it starts from. And at position 2, all we have is that same small block that's now moving at some speed. So 1/2 mv squared. I see straight away, boom, my m's can cancel out. And so I can find that my velocity at position 2, maybe I'll add a subscript 2 here to keep things organized. The velocity at position 2, which is right here, v2, that my block is moving is just going to be equal to the square root of 2gh initial. Okay, that's cool, easy enough. Now, if we look at positions 2 to 3, we want to figure out how quickly the block and rod together are going to be moving after the collision occurs. Alright, so now we're looking at conservation of momentum. And so, because we're going to be going from linear to rotational, this is where we get that kind of tricky thing when we try to do conservation of angular momentum, L initial equals L final. For something like this small block, or the bullet that we saw in last homework or in class, we can say our L initial is just going to be mv times r, the radial distance, which in this case is just the length of the rod. That's the total angular momentum. We derived that in class. If you don't remember, look back in your notes. But mvl will be the momentum brought into our system by the block, and then the final momentum is just going to be equal to I of our system multiplied by omega after the collision. Maybe I'll do a subscript omega 3 since that's at 0.3. Okay? So we can find what our omega is, omega 3, if we just figure out what our I value is. So we know M, we know L, and now V we found right up here, right? We can plug this V in, so that's the square root of 2gh initial, all divided by I. Well, that's cool. What is I? Well, that's what we need to figure out. So, the I in this case, maybe I'll step off to the side and switch to a new color over here. The I is going to be equal to I of the rod, which we've learned I of a rod is 1/3 m, the mass of the rod is capital M, times L squared, and the inertia added by the block can be thought of a point mass at a distance L away, so it's going to be plus mass of the rod times L squared. So now we can write omega a little more accurately. It's going to be equal to ml square root of 2gh divided by 1/3 capital M L squared plus little m L squared. And you can see you can do some L canceling if you want to make it a little simpler, but you have an omega value. Okay, that's how quickly it's rotating. Cool. So we're still not even there yet. Oh boy, howdy. Okay, so now we want to look at our final step, which is going from points 3 to point 4, where we're going to use energy again in an attempt to figure out what our H value is. Okay, so again, we're trying to figure out, for those of you that don't remember, this H value here. Alright, if you're not really clear what that H value represents, I'll go back up to my picture. That H value is this height, the difference between this location where our block ends and this location where it started. So this distance here, that is our H final that we're trying to find. Okay? And so we need that in order to find this D value over here, right? So, let's figure that out. I keep saying D value, and it makes me think of like decreasing the value. I'm devaluing this problem. No, anyway, sorry. So, let's go ahead and look at this. So what kind of energy do we have at point 3? Well, that's when the objects are rotating together, rotational kinetic energy, so that must be 1/2 I omega squared. Oh look, we already know what I is, so we're going to be able to plug that in down there, and we know what omega is right here. Oh boy, so we can plug that in as well. Okay, and then that's going to be equal to our gravitational potential energy at the end. So let's think about gravitational potential energy. This is what, well, one of multiple places that confuse people a little bit. So we can clearly see for the block here, this block gains a gravitational potential energy of mgh final. Okay, so let's start with just the block. It's mg times this h final. But what about the rod? Does the rod move up the exact same distance? Does it move up that same h final? So let's consider the center of mass of our rod. Here's the center of mass of our rod. Here's the center of mass of our rod. It's halfway up the rod. As it swings, it's going to have an increase in height exactly equal to half that of the increase in height of the block. So this value here, and let's get a new color, this h distance here, well, that is way off with hitting my dots, but anyway, this h distance here, I'm just going to erase and redraw that, sorry. Okay, so if we look at the center of mass of the rod here, and then the new center of mass of the rod here, this distance here, because it's halfway up the rod, is actually going to be h final over 2. It's going to increase in height half as much. So the increase in gravitational potential energy of the rod is going to be m of the rod times g times h final over 2, because it increases by half. So plus m g h final over 2, because the rod only increases half as much. So, this is crazy, and my video's pretty long, so some of you are itching to get to doing the physics yourself. But here, we should be able to solve that for h final once you have omega and I. And once you have h final, then you can come over here and figure out what your angle theta is. Now that, my friends, is a box-worthy problem. Best of luck. Let me know if you have additional questions.